Good afternoon, everyone. My name is Kelly, and I'm going to present on one of the works that we have been developing in the photonics group at USP of São Carlos, which is studied the femtosecond laser processing of TEOS graphene oxide for sensor applications. To introduce, femtosecond laser micromachining is a process by which pulse from a femtosecond laser are used to induce micrometers sized structures on the surface or in the bulk of solid materials. Energy is transferred from an optical field to a material, causing ionization of a large number of electrons, inducing permanent changes. In our lab, we've been using this process to create functional structures in a wide range of materials. I'm going to talk about the laser induced for transfer or just lift. That is a process that allows with high resolution the deposition of a small amount of material in solid or liquid phase. In the process, a thin film, which is the donor material, is placed in close proximity to an acceptor substrate, and the laser is focusing on the interface of the substrates, ejecting and printing materials by the absorption of the laser pulse. The technique is simple, fast, of low cost, and also an alternative to the traditional photolithography with no need of photomasks and clean rooms. The technique is little investigated in solid materials due to the difficulty of controlled deposition, and has been applied with femtosecond laser pulses to improve the resolution of the deposited structures due to the multiphoto absorption effect, maintaining the properties of the donor material by reducing thermal effects. As donor material, we used films fabricated by the social process, which is a method of obtaining vitreous or ceramic materials through the preparation of a sol, followed by its gelation and removal of the liquid phase. As advantages of using the process, we can mention the properties resulting from chemical homogeneity, purity, the low cost involved, the possibility of preparation at low temperature, and easy modeling. About graphene, their properties depend very much on the quality of the material and type of defect, being strongly affected by the production process. However, high graphene quality may not be easy to control, and multi-layer systems containing layers of graphene are also fabricated, presenting some advantages in a number of applications, including chemical sensors, biosensors, and supercapacitors. In the study, we used the tetratiortosilicate as a precursor, which we call TEOS. The matrices were synthesized using the Tasso process through the hydrolysis of TEOS in acidic medium in the presence of graphene oxide. The films were prepared from the sol by the spin coating technique, resulting in films of approximately 1.4 micrometers. For the lift process, we used a carbide femtosecond laser at the wavelength of 1030 nanometers. And with aid of a microscopic objective, the lasers focus at the interface of the donor and the receiver substrate. And the both substrates are maintained in contact and placed on a XYZ stage, moving at constant speed, allowing the fabrication of different geometries. As first results, after the material deposition process, groups of lines were transferred to evaluate the influence of the pulse energy on the width of the lines for the lift process. And by the optical images, we observe that the lines are reproducible, and we can see a controlled deposition, increasing the line width that increases the pulse energy. We confirm by the scanning electron microscopy images, in which we can observe a decrease in particle uniformity when we applied higher pulse energies. From the microscopy images, it was possible to analyze the influence of pulse energy on the deposit lines and to determine the best deposition conditions. For each transferred group of lines, it was possible to measure the medium widths ranging from 1.6 to 2.2 micrometers. From these results, it was also possible to determine the threshold energy for deposition of 140 nanojoules. To investigate the morphology of the lines produced by femtosecond lift, an area was inspected by atomic force microscopy, and the profile reveals that such lines present a thickness of about 400 nanometers. And also we've determined the average roughness of 40 nanometers. To analyze the nature of the transferred material, if there were any structural changes, we performed Raman spectroscopy in both on the donor material and the transferred material to be able to compare. And as I wanted to see the influence of the process on graphene oxide, I obtained the ratio of the intensities of graphene oxide D and G bands, which is higher for transferred material, which can be explained as a decrease in the sp3 domains of the graphene oxide, indicating a reduction process. Regarding the shift of the G band, some studies indicate this shift to higher frequencies during the amorphization of graphite with the presence of double bonds. To perform the electron measurements and confirm that material became conductor, I transferred an area with the lines close together to fill the entire area between gold contacts. Applying different voltages and measuring the current, the result was an ohmic behavior. And with that, I calculate the resistance and found the electroconductivity with respect to geometric pattern. And value of 3 orders of magnitude greater than the donor film was determined. That indicates an improvement in electrical conductivity after the transfer process, supporting the results of the Raman measurements, since graphene oxide is more resistive. So after all this characterization of the transferred material, we have fabricated 3 types of interdigitated electrodes with different separations between the fingers of 10, 20, and 30 micrometers. The impedance of the system is measured and the response is analyzed to cluster similar behavior and distinguish different liquids. The capacitance of the electrodes increases from the electrode 1 to electrode 3, which is in agreement with the distance between the fingers. And conversely, the resistance decreases from the electrode 1 to electrode 3. The collected data were treated using the principal component analysis which allows a reduction in the dimensionality of the data without losing important information. And it's possible that the sensor fabricated is capable to discriminate the solutions analyzed without any superposition between them, demonstrating the potential of the electrodes for using an electronic tongue sensor. The electrodes were able, through the impedance data, to separate the different heavy metals in terms of 3 concentrations tested. And as conclusions, the lift offers some benefits such as low production cost, high processing speed, and the versatility of producing several geometries without the need of automasks, clean rooms like lithography. We have demonstrated the transfer of the composite TEOS graphene oxide in a single step, and at the same time reducing graphene oxide in a controlled and localized way. And the microcircuits enabling the calculation of the electron conductivity, increasing the value for the transferred material. And the interdigitated electrodes were fabricated, and the final step was to carry out the tests for application in electronic tongue type of sensor, capable of detection of the heavy metals in different concentrations. I would like to thank you for the attention.